Today's lecture is on Euler and Euler's identity. So I'll just write that here. Okay, so my first question to you guys is, when we think of the most fundamental and important math constants, like what are we thinking of? Like what kind of numbers come to mind when I first ask that question? Yeah?
E.
Yeah, E, there you go. E is extremely important, right? E is the base of the natural logarithm. Yeah, what else?
Pi.
Pi, there you go. Okay.
Planck's constant.
Okay, Planck's constant, yeah, I think it's the h with a bar, right? I'm not exactly looking for this one. This one is important, but I'm generally looking at just these two right here, plus another one. And that other important constant is I, right? Where I has the property such that I squared is -1, right? Pi is the ratio of the circumference to the diameter, and E is defined in various ways, right? It is like the sum as n goes from 0 to infinity of 1 over n factorial. It's also defined using a limit. And it's also the base of the natural logarithm, and it has the property such that e to the x, the derivative of e to the x is e to the x, right? So these are all extremely important numbers in math. Also, another really important number is 1, right? That's, yeah.
Another important number is when you combine the two powerful math constants together, e to the pi is 23. So that should be up there.
Yeah, so e to the pi is a number, it's like approximately like 23.14. Okay, this is actually somewhat related to what I'm going to go into. So basically, with all of these numbers here, e pi, I, 1, there's actually an equation that combines all of these. That's extremely simple. And that equation is called Euler's identity. So I'll write that here. And this equation simply says that e to the I pi plus 1 is 0. And that's my entire equation right there. E to the I pi plus 1 is 0. Okay, so this is kind of weird how I'm like combining a real number and an imaginary number, and all of a sudden I get another real number or a negative number. And so today I'll just try to break down exactly why this works and how we got here. Okay, so I'm going to start over here. And so let's just say that we have a function. And let's just say that our function is cosine theta plus I sine theta. So this is a function with complex numbers in it over e to the I theta. And I'll show you why I chose this specific function here. Okay, so this function here, I can rewrite it as e to the negative I theta times cosine theta plus I sine theta. And, okay, so I want to look at some of the properties of this function. So if I actually differentiate this function, I get, by using the power rule, I'll get this. And then I have my other term plus e to the negative I theta times, and the derivative of this, which is negative sine theta plus I cosine theta. Do you guys see how I got there? I just used the power rule and differentiated this to get this, right?
Okay.
Okay, if I expand this out, I get negative I e to the negative I theta times cosine theta minus I times I is plus 1, right? So plus e to the negative I theta sine theta. That's this part here expanded. And then I have minus e to the negative I theta sine theta plus I e to the negative I theta cosine theta. Okay, so now we have 4 terms after we've differentiated this arbitrary function, this in polar coordinates, right? So we have this term, this term, this term, and this term. And do you guys notice what happens here? Do you guys notice that this term cancels with this term? Because this is negative I e to the negative I theta times cosine theta. This is positive, same thing, right? Notice how these two terms also cancel? So that entire thing just becomes 0. And so basically what I've done here is I've differentiated some function that I've come up with. And that function has gone to 0. And so what does that tell me about my original function? If I differentiate something, what about the original function makes it go to 0 if I differentiate it?
It has 0 slope then?
Well, no, it's a constant, right? Like, yeah, 0 slope essentially. right? So f of theta could be like 5, it could be, you know, negative 1,000, right? All of these are just constant functions. And if I differentiate them, they go to 0. So what that tells me about this particular function here is that cosine theta plus I sine theta over e to the I theta is actually just a constant. It's not some other function. It's just a constant for all theta. Okay, so if I want to rewrite this, I can say that e to the I theta times k is cosine theta plus I sine theta. Okay, and in order to actually find out what k is, I can substitute a value for theta, right? I could maybe say theta is pi over 2, theta is pi, theta is 0. The easiest one to plug in to find k is actually just theta equals 0. Because here's what I get if my theta equals 0. I get e to the I times 0 times k is equal to cosine 0 plus I sine 0. Okay, so this right here, e to the I times 0 is just e to the 0, which is just 1, right? Cosine 0 is 1, and this is, and I times sine of 0 is just I times 0, which is just 1, or sorry, 0, right? So now what I have here is, I just have k equal, this is 0, this is just 1. So essentially what this right here says is that, and this doesn't just hold true for theta equals 0, this holds true for all theta. So theta from 0 to 2 pi. And so my actual function is that here, if I rewrite it over here, I'll get my eraser. So my actual function is just that if k is 1, cosine theta plus I sine theta over e to the I theta is 1. That's what I've shown here, right? Just by plugging it in and differentiating it. And so I can rewrite this as just e to the I theta is cosine theta plus I sine theta. And so now I have this weird relationship between my exponential in the complex plane and my sines and cosines in the complex plane. And so this is a relationship that's used a lot when we're dealing with like Fourier series or whatever. Okay, does that make sense so far? Mm-hmm. Okay, so now all I have to do is, if I want to find out what is e to the I pi, what is that equal to? I can plug in pi for theta, right? If I plug in pi for theta, I get e to the I pi is equal to cosine pi plus I sine pi. And we know what sine pi is, right? Sine pi is just 0. I sine pi is 0, because I times 0 is 0. That's 0. Cosine pi is -1, so I get e to the pi, I pi is equal to -1, or e to the I pi plus 1 equals 0. And that's basically the overview of how we got to this equation. There's obviously more in-depth proofs, like with power series or with like geometry, but this is just kind of the simplest proof that I could find. So, yeah. Does anyone have any questions? Okay. Do you guys want me to go over like a just kind of what the cosine sines and cosines look in the complex plane and how it kind of looks like visually? Yeah.
Wait, so where did that original function, like the f of theta equals the cosine theta plus I, like, well, all that like come from? Is that like a kind of it was just kind of like a guess to see if that would work out, or was it like how did they come up with that originally and know that that would?
So I don't know exactly how they came up with this originally, but I know that they found like relationships between like what happens like how e. If you differentiate e to the theta, it's always going to be e to the theta. Whether and you're going to have multiplied by some constant, right? But cosine and sine, they kind of switch back and forth when you differentiate them. And so that's what they're doing, is they're using that they're using that property where e stays the sine, but cosine and sine are different.
Oh, because they just oscillate back and forth, and e just stays.
Yeah, exactly.
So that's why they picked those functions.
Yeah, and the actual proof behind it, a lot of like the more in-depth proof is with like power series, and so you can actually prove it just by plugging in I times x within the power series for sine and cosine. But I just wanted to go over this one because it's a lot faster.
Yeah.
And like basically, if we draw this out right in our complex plane, if this is our real axis, our imaginary axis, and we have our unit circle, we agree that all points on the unit circle are cosine theta plus I sine theta. Like that's just my definition of a complex number. So if theta all goes all the way to pi, what's my value here? It's going to be -1 plus 0i, which is just -1.
Yeah.
So same thing, yeah, it's just different ways of looking.